fund, to many people interested in medical research, means only one thing: the Imperial Cancer Research Fund. Now reckoned to be the largest independently financed research organization in the whole of Europe, it supports a quarter of all cancer research that takes place in the British Isles. This look at the work of the fund touches on what cancer is, but it's not really concerned with the statistics or too closely with the nature of the disease. It's more about the people who work on it and the way in which the money contributed by the public is eventually spent. That advertisement appealing for funds in the Times has an interesting precedent, incidentally, for it was in that newspaper that the idea of a cancer fund was first aired. In April 1902 appeared a letter suggesting a cancer fund. It was signed by a distinguished company of public figures from Parliament and elsewhere, and was followed by an anonymous offer of support. Within weeks, both the Royal College of Surgeons and the Royal College of Physicians had offered their approval. On July the 4th, the Cancer Research Fund, as it was then known, came officially into being at the old examination hall on London's Victoria Embankment. Heading the first team was E.F. Bashford, who remained the director for the next 12 years. Looking back at the minutes, one can see that distinguished support was evident from the beginning, even if the £11,000 total seems small now alongside the £6 million or so handled annually by the fund today. The unit at Mill Hill became the centre of operations in March 1936. The present head of this laboratory is the former chief of America's Cold Spring Harbor Laboratories, Dr. John Cairns.
The lab here was built, I suppose, in the early 1930s, and like any old building, its parts eventually start to fail, and we have in the last 2 years been renovating it from top to bottom, predominantly for a group of new people coming in, new young scientists who have been recruited since I became head of the lab at the beginning of 1972. We use machines instead of people now. You can get machines which will work like devoted slaves for you, changing samples every couple of minutes for the entire weekend. And that is a great saving. The result that the individual scientist now can produce results at a much faster rate than his predecessor.
Results come from research work at the bench, and in one of the newly equipped laboratories, geneticist Julian Gross is working with amoebae. These independent cells don't cause disease. They live in woodland soil. And though independent, each separate cell, on receipt of a chemical signal sent out by one of them, heads towards a common center. And then a remarkable transformation takes place. For this organism, Dictyostelium can exist in two quite distinct forms. Under the high-power lens, we can see what's happening. The individual cells are beginning to work in concert, to function almost like a multicellular, higher organism. Instead of living free, they produce a rounded, single body. As the last few cells seem to hurry into position in this speeded-up filmed record, it's hard to imagine that the single amoeboid cells ever existed. Looked at from the side, the slug-like nature of this new organism is very clear as it begins to crawl along. Dr. Gross studies Dictyostelium because the way random, individual spreading cells can become organized is almost the exact converse of what happens in cancer, when coordinated cells in the body run riot. By comparison, the speeded-up appearance of normal mammalian cells, on the right in this culture, is clearly more ordered than the newly transformed cancerous cells on the left. It is this spreading, infiltrating behavior that makes cancer such a serious disease. And because cancer cells are the patient's own, it is not easy to kill them without harming healthy cells at the same time. So the challenge of cancer research is considerable, and so are the problems of choice faced by the research worker, people like Dr. Cairns.
I have no idea what the answer to cancer is going to be, nor when it is going to come. We don't really know in what form this answer is going to come, and we cannot tell whether we should be supporting what's normally called cancer research, or whether we should be pumping money into organic chemists, or into statisticians, or what. And no organization, however large, has enough money to be able to support everything.
Today's headquarters of the fund are nearer central London, and stand facing the tennis courts in Lincoln's Inn Fields. It is from this spacious complex of offices and laboratories that the fund's operations are now coordinated. How does the Director of Research, Dr. Michael Stoker, weigh up the question of priorities?
The big problem of how to distribute one's effort is shared out among lots of us, and it finally evolves really as a consensus of opinion after lots of discussion among many people, many of my colleagues, including Dr. Cairns, of course. He's quite right that we can't support everything. No organization can do that. You can really think of two classes of research and progress in cancer. One class deals with cancers in which there's really rather remarkable progress being made at the moment due to successful research. Cancers like, leukemia, certain types of cancer of the womb, and cancers of the glands, and so on. There the outlook is getting better and better, and so one sort of research is to plug this hard, to look for returns as quickly as possible. Then, unfortunately, there are the more common cancers, cancer of the lung especially, which we know how to avoid now, but we don't know how to cure it. And these common cancers, are the things that really most people die of who get cancer, are the ones that require a much longer-term approach. And that means trying to discover about the single living cell that started the whole thing off.
Of course, you don't only direct research, you also take an active role in doing it yourself.
Well, I enjoy it. I think one does what one enjoys, and it's a good mixture.
Would you like to come and have a look at the automobile rest, Michael?
Ah, some there. I hope.
5%.
I see.
On this occasion, Dr. Stoker is examining cultures of breast tumour cells from patients at the Guy's Hospital unit, the ultimate intention being to determine the sensitivity of a particular patient's tumour to treatment with drugs or hormones.
Cells piled up at the edge.
There's one.
Yeah.
They're really quite... Because you've got...
That's from the clear.
Yes. This is the rolling edge again. And...
Discussion, international discussion, underpins progress. Dr. Taylor Papadimitriou has come from Greece.
We can transform a normal cell with viruses or chemical agents, and this cell can give rise to...
A British cell regulation specialist, Philip Rudland, works in the group now headed by the distinguished Italian-born Renato Del Becco, the fund's deputy director.
There are a number of criteria we can use. For instance, first of all, they look different. Morphologically, they look different.
In the same group are Yoshi Ito from Japan,
or transform cells will require much less serum for the growth, and things like this.
It's known that serum has some promoting factors which are...
Louis Dasua from Argentina.
in normal cells.
Yes, well, maybe this is another possibility to look at, possibilities of...
And Dr. Minnie O'Farrell, who came to the fund from Geneva.
Act in similar ways, but maybe different in their specificity.
Lots of these factors seems to come from the pituitary gland, and you think that there are still room for searching in there to see whether there are factors which we don't know yet?
The asking of fundamental questions like that is something that becomes easier with experience. Finding answers, however, is painstaking more often than it is fortuitous. The keeping of detailed records is a fundamental rule of the game, one which all the players observe. But though this imposes some strictures on research, there is excitement and enjoyment too. The poster pop singer's exuberance derives in some ways from total commitment of a similar kind. Members of the public who visit the fund often find similarities between their own jobs or their commitment to a hobby and what drives scientists in science. When Jim Smith tosses ideas around with Ian Mannering, Liz Symes and the Australian Ben Martin, It's not all weighty and ponderous.
It's the same thing with the uterine cultures. You don't get, despite your experiment, you don't get cell division.
I do get cell division.
You did.
I did.
Well, I mean, look, this is why I come back and say the main problem is likely to be physical rather than chemical, because for how long has tissue culture been going? People have been stirring in the most magnificent witch's brews, you know, chicken embryo extract, and all this sort of stuff, and murmuring incantations, and you still have these problems with primary cultures.
All right.
And yet nobody, in relatively speaking, no one has looked at physical problems.
Well, let's say then that it is a problem of geometry. I mean, how would you simulate that?
See,
This could be very, very important.
Yeah, but
You
even
can
if you grow,
successfully separate the two things.
yeah, but even if you grow them in mixed cultures, it's only the stromal cells that grow, if anything.
So far.
So far.
But I still think the proper experiments haven't been done.
No, maybe if you grow a layer of stromal cells on the bottom of your dish, which seems fairly feasible, and then stick your epithelial cells on top.
But you tried that with the uterine cells, and the damn things
but I
didn't
didn't
work.
try it on epithelial stromal cells. I tried it on irradiated fibroblasts and things like that.
It was a Burkish thing to do.
It was a Burkish thing to do. Burke suggested it.
That's right, too.
Such informal discussions are perhaps not what one thinks of in connection with research, and much of the expenditure in cancer research goes on apparatus, such as this Beckman sequencer. Dr. Mike Waterfield can now use it to remove the amino acids which make up the protein components of cells like beads on a string, the sample being spun at high speed in a calibrated cup. To most biologists, even this sophisticated device is unfamiliar. But the electron microscope and its use in observing viruses is surely familiar by now to everyone. Many workers all over the world use viruses to transform non-malignant cells into cancer cells in the laboratory. Yet no certain example of a virus causing cancer in man has yet been found. One of the people looking for the hidden traces of viruses in cells is Dr. Robin Weiss.
Well, if there are viruses associated with human cancer, they're difficult to find. Human cancer cells are not actively releasing viruses, but we can't think of any leukemia in animals that doesn't have a viral cause. So we do believe that it's important to study animal viruses, and we're particularly concerned to study the natural history of the viruses in wild populations of animals, because that more resembles the situation we may expect to see in man.
Precautions against possible infection are always necessary in these virus laboratories and range from warning signs to protective clothing and air filters. But apart from the uncertainty about the cause of leukemia, what of its cure? Cancers of the white cells, such as leukemia and Hodgkin's disease, are now being successfully treated. Dr. Alistair Thompson studies leukemic lymphocytes from the blood. These two stained white cells in this typical field of view are what normal blood shows us under the microscope. In leukemia, some cells escape control and then go on to produce vast damaging populations instead. A slide from a case of lymphocytic leukemia shows this dramatic change. Colchicine is a compound that can selectively kill these cells in the test tube, but not in man.
Colchicine was obtained from the autumn crocus. It has in fact been used for centuries to treat the symptoms of acute gout, funnily enough. It is permissible to give this drug to patients, in fact, in very small amounts, but they are not sufficient to give any therapeutic benefit.
Biochemists try to predict the activities of new drugs from their structure. But does the head of the Fund's Cancer Chemotherapy Unit, Dr. Kurt Hellman, feel confident of our ability to predict drug activity?
I wish we could do it, but we simply have no means of predicting what a compound is going to do when it gets into man. Well, the United States National Cancer Institute has looked at some 300,000 compounds, and the prediction of these compounds as a result of animal tests has been proven wrong in a great number of cases. One of the great difficulties also is that compounds are broken down by man in different ways, and this makes it very difficult to judge what effect any compound is going to have.
It is the cancer patient who is the ultimate arbiter of treatment, of course. And at St. Bartholomew's Hospital, Barts in London, is one of the Fund's extramural research departments, the Medical Oncology Unit. They have been applying drugs which, a little like colchicine but without those damaging side effects, can kill cancerous white cells in diseases like leukemia and Hodgkin's disease. A few years ago, 90% of the victims of Hodgkin's disease died in a 5-year period. Now the position is reversed. 5 years after diagnosis, 90% are alive, and most will permanently be cured, according to the unit's director, Professor Gordon Hamilton Fairley.
The headquarters of the ICRF are concerned with very fundamental research, and it is all laboratory research. We, on the other hand, do some laboratory research, but it is all in relation actually to patients and material taken from patients. So what happens to them is they arrive at the hospital, and the first thing that usually happens is they have a blood count. And we look at the result of the blood count, and we see them later in the day, and we then examine them. They may have x-rays as well, but we try to find out whether or not there is any evidence that the disease is active.
Okay, just gently and take a deep breath in and out. Once more, right in. That's it.
We then decide whether they should have treatment on that day, and if they should have treatment, this is started.
How are you?
Fine, thank you.
Thank you. Could you put us in this arm today? Quite good. Have a little boy.
Same as usual.
They will then usually have 2 weeks treatment, largely consisting of taking tablets, but with a few injections interspersed. And during that time, they may have 2 more blood counts, 1 a week later and 1 2 weeks after that. We would then send them away and not see them for another month, when they might have another course of treatment.
Splendid, and another one.
Here's a normal chest X-ray with the heart shadow like this. Here, the heart shadow is virtually obliterated by this great big mass of tissue which is situated, as you say, at the front of the chest. Now, we've done various blood tests and so forth and still failed to get a diagnosis. What ought we to do then?
Well, you'd have to take a biopsy, that is, try and remove a small sample of this lump.
Yes, indeed, and that's been done, and perhaps you'd like to tell us what the answer is.
It was found to be Hodgkin's disease.
Yes, that is correct. And basically there are 2 ways in which it can be treated. It can be treated either by radiotherapy, that is X-ray treatment, or by what we call chemotherapy, that is a mixture of various drugs. What do you think would be the most likely form of treatment here?
Well, in this lady, since the mass is so widespread and the symptoms so serious, I would use chemotherapy.
Yes,
on deep X-ray.
Yes, I think that's right. And I think particularly that's right because that mass is so large that it's pressing on vital structures like the major airway, the trachea, and the heart. And this is one of the reasons that the patient was admitted to hospital looking slightly blue as opposed to pink. In other words, the blood was not getting enough oxygen from the lungs. So indeed, that was what happened. She was given treatment with 4 different chemicals together, and 1 week later, I think you can possibly see a difference.
Well, the mass is greatly reduced in size on the X-ray.
Yes, that's right. This is, in fact, a very impressive change, and now you can just see that actually there is a heart in the middle here. And after a few more weeks, that will, what we call regress, that will become invisible. And this patient, in fact, stands a substantial chance of being cured of this condition altogether. If you are going to try different treatments on patients, they have to be very intensively studied, they have to be very carefully looked after. And this, of course, involves much more staffing than would normally be provided, for example, in an ordinary National Health Service hospital. Then you have the other aspect, which is literally capital outlay, and this is deliberately doing research on different aspects of the disease in order to find out information which may then become relevant to what you're doing at the moment. And again, money is required for that.
Some of the fund's money for the uncovering of new relationships and new ideas on treatment goes towards collecting and storing specimens. Liquid nitrogen tanks can hold cells in a state of suspended animation for prolonged periods, certainly for years. During the fund's breast cancer screening trial in Guernsey, for example, 10 tons of specimens were flown to London over a 14-year period for storage. This particular container holds blood cells in what is, in effect, a giant vacuum flask. Some of Professor Hamilton Fairley's patients are treated with these cells to stimulate their own defensive responses against foreign proteins. The idea being to encourage the individual to generate antibodies against his own cancer cells. But since cancerous cells, as we've seen, are the patient's own, this immunological approach is not as successful as it is against invading bacteria. But it is becoming an increasingly useful approach to use, particularly in combination with drugs or other forms of treatment. Unorthodox shortcuts in research work often give rise in time to routine and repeatable procedures. And the testing of cells against successive dilutions of active agents has become widely used in many branches of science, from cancer research to inorganic chemistry. Suspensions of cells in these plastic Terasaki plates clump together, agglutinate, if they possess identifiable antigens on their surfaces. And it's these that stimulate the production of defensive antibodies. So we can demonstrate their existence without the need for analysis as such at all. But if plastic plates are inexpensive, then this cell separator at Bart's is at the other end of the cost scale. Some patients under treatment suffer low levels of the blood platelets that are necessary for coagulation and the control of bleeding. This machine removes platelets quite harmlessly from a healthy donor. Today's volunteer, Mr. Keane, is a member of the Red Cross. More often than not, a relative of the patient will donate some platelets.
Here it goes. And that's it, all finished. Thank you very much indeed for coming. That's really super.
I mentioned how the immune approach to therapy can encourage a patient's own cells to destroy cancer. And it's at the London University Department of Zoology that Professor N.A. Mitchison heads the tumour immunology unit of the fund, designed to try and understand what it is about cell surfaces that stimulates the production of anti-cancer antibodies.
Well, we're concerned here with the antigens which are present on the surface of tumour cells, particularly in leukemias. We have 6 scientists here and 9 technicians, and then we have a number of visitors from abroad. I think we have 10 of those altogether. They come, for the most part, from North America, from the United States or Canada. But we have one girl from Japan and a man from Israel. They're fair scattering, several from the continent, of course.
We have seen how one kind of blood cell can be sorted out in the separator and heard how the cell surface can stimulate the formation of antibodies. But this machine, used by David Capillaro, provides the ultimate facility, for it not only identifies cell surface components, but sorts out the cells one by one. After preparation, the stream of cells is run through a nozzle that is so fine it allows them only through in single file. A laser beam, shone through the stream, picks out individually labelled cells of different types. If we look closely, we can see that the stream of droplets falls between 2 metal plates, and then emerges from the bottom in single file. When the sorter is switched on, the plates become electrically charged, and the differently labelled cells, identified by the laser, are attracted by static electricity into separate test tubes. The sensing apparatus gives the total number of cells collected, and also plots a graph of their distribution, thus giving one purified samples of cells with specified characteristics for the very first time. Thomas Guy, immortalised in sculpture, still watches over the hospital that bears his name, where the fund maintains the headquarters of its other extramural unit. This one specialises in new approaches to the treatment of breast cancer, under its director, the surgeon, John Hayward.
The traditional orthodox treatment for breast cancer has been, since the beginning of this century, the operation of mastectomy, which essentially means removal of the whole breast, with or without the glands that lie under the armpit. Now, a lot of people have challenged whether an equivalent result can be had from a less mutilating operation than mastectomy. That is to say, removal of the tumour itself, conserving the breast, possibly with the addition of some form of other therapy afterwards, like radiotherapy or possibly chemotherapy. And we've been running a trial on this over the last 15 years to see if a less mutilating operation would be feasible. I mean, if you look back in the writings of the end of the last century, beginning of this century, surgeons in those days were dealing with a totally different situation from what we're dealing with now. And what we've been trying to find out, essentially, is should the treatment that we are applying to patients change in the same way? Because up until, 15 years ago, the treatment that we applied to women with breast cancer was precisely the same as it was 75 years ago.
This is the breast unit built onto the old New Cross Hospital where Mr. Hayward's patients are now being treated. At the moment, they're just starting work on the use of drugs at the time of the first operation to prevent the chances of a later relapse. And this brings us to the most human question of all. When an otherwise untreatable cancer can be controlled, say, by hormone therapy, what is it like for the doctor who actually witnesses it? Christopher Franks, a Fund research fellow here at New Cross, can recall some examples.
There are two cases that come to mind. One is a lady of approximately 75 who was left with a very difficult social problem, had to bring up both her grandchildren, and she presented at our clinic about 6 months ago with multiple skin nodules, and in the following month they showed a rapid increase. So we put her on a course of hormone treatment. These gradually disappeared, and when she was last seen, she was completely free. The second lady is a much younger lady, about 49, presented to our clinic with rapidly increasing dyspnea, shortness of breath, and X-rays showed that she had profuse infiltration of both lungs. She again was put on hormone treatment, and for the last 6 months now has been completely free of any evidence of involvement. And all I can say is I got a tremendous thrill from seeing both these patients recover. One is at work, in a full-time job, and the other is at home, completely free from any symptoms.
Such success stories for so many patients remain the exception rather than the rule, and getting nearer to an answer for the rest takes money, devotion, and time.